The agenda is starting into the brave new world of concurrency. So we're done with Java, or I'm sorry, with Python, and we're back actually into Java for the next 2 weeks. So we have our next 4 lectures, next 2 weeks. We are talking about concurrency mechanisms in Java, and we are going to be talking about Java's thread. So we're doing it in Java. So we're going to be talking about Java's thread mechanisms, Java's locking mechanisms, and synchronize, how you can basically synchronize. We will be talking about sockets, which are ways that allow you to communicate between 2 different computers. And then some of Java's high-level concurrency features. That were introduced in later versions to make handling concurrency easier. And we'll get to those basically the last of the 4 lectures. Locking and synchronization will give you the ability to answer the questions 1 and 2 on the homework assignment. Sockets will give you the ability to answer question 3, where you'll be writing a talk program. I believe Dr. Plank has you write a talk program in 360, if I'm not mistaken, correct? So you'll be re-implementing that program in Java's socket and threads library. Then we have, I used to race and run a lot, so you have a simulated bicycle race for your first question, which we'll talk about probably on Tuesday, give you some ideas about how you should be tackling that problem. So today is an introductory day to concurrency in Java. So we're going to try to get through threads and our locking mechanisms today, and then hit on a little bit with deadlock and sockets on Tuesday, and probably some more with deadlock and sockets on next Thursday, and ending with high-level concurrency functions a week from Tuesday. And the best reference, so I basically, if you're looking at my notes, basically my lecture notes, my slides, so I have a number of slides for concurrency, sockets, and I have them also, yeah, my high-level Java concurrency slides. These basically summarize the Oracle Java tutorial on concurrency. So if you follow this link, you'll get the Oracle's concurrency tutorial, and basically my notes follow their 2 tutorials on that. Okay, concurrency and then their sockets tutorial. Okay, so without further ado, so we just need to agree on a couple terms. So in this course, a process will be referred to a self-contained execution environment, and a thread will be, in effect, like a subprocess, exists within a process, and it shares the process's resources with other threads, particularly memory. So you have multiple threads of execution, and they are sharing memory. So basically, the idea is that you have a process and it has things like files, memory, and then you can fork off threads, thread 1, thread 2, thread 3, and they all have access to these resources, to the same files, to the same memory. So you're going to have to mediate between them in order to prevent contention in what are called race conditions. Okay, so, but a thread looks like its own self-contained. So a thread will look, a thread is an independent, well, is a quasi-independent program that cooperates with other threads. So you already saw threads with Java Swing, where you ran main and that was one thread, and then the swing thread is where the GUI was executing. So that was called the event handling thread. So you've already had some experience with threads in this course. Okay, it's just that those threads were hidden from you, and here you're going to be explicitly dealing with them. So Java has two ways of dealing with threads. One is the low level, using either the thread class or the runnable interface, where you kind of are doing the management of the threads yourself, or high level, which is what I referred to when I talked about Java's high level thread libraries. And there you have thread executors and tasks, and Java is basically doing the management of the threads for you. You don't have to worry about starting them or scheduling them or ending them. That's all done for you by Java. So initially they gave the lower level package, more like the POSIX package in C. And then later they said, well, this is kind of complicated, so why don't we take some of the management burden off of you and introduce some higher level mechanisms. So your exercises are going, or your homework, you're going to have to all deal with the low level, because I want you to get experience with that. So there's essentially two ways that you can create a thread in Java. One is using the runnable interface. And there, what you do is it has a method called run, which will execute when the thread starts. So here I'm just having it print hello from a thread. And down here, you see that I am creating a new thread and passing as an argument to it this hello runnable class. And that is so I can create a thread by passing in an instance of this runnable, and then .start actually starts the thread. And when the thread is actually scheduled, it will call this run method. So start does not actually start the thread running. It just makes it eligible to be scheduled on the CPU. So it may start at some point in the indefinite future. So all it does is it says, I'm ready to start executing, you may now schedule on me. And when I do start running, it calls the run method. So the second way you can create a thread is to just extend or subclass the thread class. And again, it's the same method that you are overriding, the run method. And now I just create an instance of the thread and again call start. So if you compare the two, this is a little more complicated with the runnable interface. It's a little less direct because you create the run method and then you have to create an instance of the class and give it to an instance of thread. Whereas here, you just create one instance of a class. The other way, you created two instances of a class. So basically, it's easier to use the thread class to create something, but Java doesn't support multiple inheritance. So if you want to subclass some other class, then you probably are going to have to use runnable in order to implement your thread. But if you're not needing to subclass another class, it's fine to extend thread. So basically, Java had to do it this way because it doesn't support multiple inheritance. If it did, they wouldn't have this runnable interface. But that's the whole point of the runnable interface, is that it allows you then to subclass some other class and still act like you're a thread. Okay. So then you sometimes want to be able to pace a thread, to control it for things like animation, or in the first homework assignment, you're running a mock race. And so you generate a time it takes to run some leg of the race. And so then you want the thread to sleep while it, quote, runs that portion of the race. So calling the sleep method on a thread will suspend it for however many milliseconds that you specify. Now, that gives up the processor. What it also does is it does not guarantee that you will get the processor back after, say, 500 milliseconds. If I say sleep for 500 milliseconds, there's no guarantee I will get the processor back in 500 milliseconds. What it says is that in 500 milliseconds, I will be placed back on the scheduling queue, and that now I'm again eligible to be scheduled. So the problem, if you think that you're going to sleep 6 times for 500 milliseconds and be done after 3 seconds, you would be wrong, because you get what is called drift. So it's, just to make it clear, if you think, so you might start at time 0 and say at time 10, you sleep for 500 milliseconds. So now you're asleep. At 510 milliseconds, you become eligible. You're put on the scheduling queue. But you don't actually start executing. So for example, maybe you don't actually start up again until 530 milliseconds. Maybe you execute for 10 milliseconds again to 540, and then you sleep for 500 to 1040. And again, at this point, you're only eligible to be scheduled. You might not, say, in this case, pick up until 1057. So this part right here and this part right here is called drift, because you're not actually executing exactly as you wake up. You are waiting. And so, for example, you wouldn't want to implement a clock with a hand that goes says sleep for 1000 milliseconds, then move the hand by 1 second, then sleep 1000 milliseconds, because very quickly your clock's going to fall behind. Okay, so you got to be cognizant of the fact that sleep causes drift effects that you need to reckon with. Okay, and there are ways that we'll show you later that guarantee that you start up at certain times so that drift gets eliminated. Okay, another thing with threads is you want to be able to interrupt them so that they can hand back execution to the parent process. Because sometimes threads can get into very intensive computations, and you would like to be able to stop them. So there's two ways that interrupt can be invoked in order to interrupt a thread. So the interrupt method can be called on a thread. So another method can call t.interrupt, and it's supposed to notify the thread that it's interrupted. And there's two ways to handle an interrupt. So certain methods throw what's called an interrupted exception. So in that case, you can simply catch this interrupted exception. Okay. The other thing that you can do is you can call this thread.interrupted function, and it will set a status flag that can be checked by the interrupted thread, and when it checks it, that flag will be cleared. So it's easier to show an example of each. So in this one, what I'm doing is I am iterating through an array, and every 4 seconds, I'm printing one string from that array. So I'm saying for I equals 0, I less than the length of the array, first I pause for 4 seconds, which is 4,000 milliseconds. And if I'm interrupted during that sleep process, I catch the exception and I return, so I stop. Okay? Otherwise, if the try successfully terminates, after roughly 4 seconds, I print the next message. Okay? So that's how it works with the interrupted exception. Here's one where I am doing some heavy computation. And what I'm going to do is iterate again through an array. And I'm going to call this heavy crunch computation on each element of the array. And I'm going to assume it takes a long time. So after each element of the input has been processed, I check my thread.the interrupted status to see whether I've been interrupted. And if so, I return. If not, I keep going. Okay, so we can look at a more detailed example. So let's go to, see if I can, this isn't going to work. Yep. The problem is the link that you see there is slightly, okay. Okay, so here's that code fragment that you saw before, where you are iterating through that message array, and every 4 seconds you are printing a message. And here is main. So what you do is you first calculate your patience. So we're defaulting to an hour. We're willing to let that message loop run for an hour. But you're allowed to change how patient you are with the command line arguments. So you might change that. You give it some number of seconds. So that's computing your patience in number of milliseconds. So if you say, for example, 15, you're only willing to wait for 15 seconds.
Dr. Vanderzanden?
Yes.
Is it convention when you're calling sleep to do whatever seconds times 1,000 since we're doing milliseconds? Or if you have a constant, do you just do the straight 4,000 like you see there? Does it matter?
It doesn't matter to me. I'm fine with you hard coding it.
But there's not a convention either way, whether you
Not that
multiply
I
or
know
just
of,
put it.
no.
Okay. Thank you.
You're welcome. Okay. So thread message is just a, see if we can find thread message. It is just a function that prints a message, and it's also, as you notice, getting the name of the current thread so that we can figure out which thread actually is doing the printing. So it prints out the thread name and the message. So we indicate from main that we are starting the message loop thread. And you can see that we're getting our start time so that we know when we start, so that we can compute when we should be ending. Then we create our message loop thread and we start it. And we now say we're waiting for the message loop thread to finish. So we go into a while loop. So is alive indicates whether that thread is alive or has terminated. So you see inside the while loop, we say still waiting. We wait for a maximum of 1 second. And we haven't gotten to join yet, but what it says is we are going to wait until for 1 second for this thread to join with us. And then when it does, we are going to calculate whether our, so this is our current time, this was our start time, so this is the amount of time we've been executing thus far, real time, clock time. So if it's greater than patience and the thread is still running, we print out a message saying we're tired of running and we call interrupt. So now that is going to throw this interrupted exception. So the thread message thread will catch it and whine about the fact that it wasn't done, but then it will return. Okay, so after we interrupt it, we actually again wait for the thread to shut down through the join. So the join is a way of waiting, which we'll get to, and then it prints out thread message. So kind of fun to see it in its full glory. So let's actually dump that into a file called simple threads. Let's see if I already have simple threads. Yes. The first time, I'm just going to let it run. So you can see in main, it printed then thread, mares eat oats, does eat oats, little lambs eat ivy. Okay, main still waiting. And it finished everything. So there was 4 messages that were getting printed. Okay, now we'll change our patience to be 3 milliseconds. Something's wrong here. Let me check it's trying to stuff out way too fast. Is there no, oh, that's because I commented out, okay. Do it again. Okay, let's copy that file. Something is haywire. Okay, so here we go. This is better. Waiting for 4 seconds, it prints out the first one. Waits for 4 seconds, prints out the second one. Waits for 4 seconds, prints out the third one. So remember, it joined every 1,000 milliseconds, hence why it printed 4 of them. Now we're going to only let it go for 8 seconds. So prints the first one, and it didn't even get, because 8 seconds didn't quite give it enough time to even print the second. Actually, it did. Mares eat oats, does eat oats, so just barely got under the 8 seconds. Then, after the 8 seconds marked, main said, I'm tired of waiting. Thread 0 complains I wasn't done, but still terminates. Okay, so let's actually show you join first, and then you can ask any questions you might have. Okay, so join allows one method to wait for the completion of another method, or so if you don't give it an argument, it waits indefinitely for that thread to finish execution. If you give it a limit, like 1,000 milliseconds that you saw in the example, it says, I'm only going to wait for that long, then I want control again. So it's like saying with a friend, I'm only going to wait for you for, say, 10 seconds. And if you're not here by then, I'm taking off. Whereas if you give join without any argument, you're basically committing yourself to wait for your friend indefinitely until your friend arrives. So giving join an argument says, I'm only willing to wait that long, and then I want to pick up execution again. So join, just like sleep, gives up the processor to another thread. But then when join terminates, you're eligible for execution again. And remember that a CPU time shares processes. So a thread, like that message thread, doesn't get to run forever. When you say that I'm only going to wait for 1,000 milliseconds and then I want to be rescheduled, that eventually causes the other thread to be temporarily paused as you get your time slice. So remember, a CPU time slices, it doesn't, once you have the CPU, you don't get to run to completion. You get it for some amount of time determined by the CPU or the OS's scheduling policy. And then when your time slice is up, you're shuffled back into the scheduling queue and some other process gets it, which is what's happening here with main versus that message printing thread. Main, after 1,000 milliseconds, eventually gets the CPU again and does its thing. Okay. So join, do I have it here? No. So join creates what's called a happens before relationship. So join creates a happens before. So for example, if you say, if you're in B, you're running, and you say a.join, you are saying that A happens before B. So in particular, anything that goes after the join is going to occur after A has terminated. So join is a very simple synchronization method between two threads. It ensures that, in this case, A finishes before B completes its execution. So a very simple synchronization method. Okay, so why do we need synchronization? So there's two big reasons. The first of all is remember, we have shared resources. And one possible problem is you get a contention for shared resources, such as a counter. So you need to control the order in which two or more threads are able to access a resource, because otherwise you could end up with some kind of inconsistency. Okay, but a very simple way of thinking of a race condition let's say you have two threads representing two buyers. So we have a product whose quantity is 1. And we have two threads representing two different buyers. So we want to ensure that only one of those two buyers gets the product. We can't guarantee that product for both buyers. So one thing with synchronization is to ensure that only one of these two threads actually gets the product, and that we don't inadvertently give both threads the product. Okay, now we can't really control which one gets it. So that is a race condition, because a race condition, okay, it's arbitrary whether A or B gets it. Okay, so you get non-deterministic outcomes based on which thread gets first access to a resource. So one thing that two threads can do is cooperate using join. And that creates that happens before relationship. So thread A could defer to thread B and join, do B dot join, in which case B would get the product, because A would for sure happen after B. So join is a very simple way of sequencing things to control these race conditions. Okay, the other thing that can happen if you aren't careful is you can get memory inconsistency. So let's say that thread A relies on thread B performing a write before it does a read. In that case, you definitely want to ensure that B happens before A, and joins is a trivial way to handle that. Fork, which is forking off a new thread or new process, well, we'll call it a new thread, is another way of doing that. You might not start A until B has finished. So basically, you could also delay forking the A thread until B did its write. Okay, so Java gives us 3 ways to synchronize accesses to resources: synchronized methods, synchronized statements / locks, and atomic variables. So the first kind is synchronized methods. So here's a synchronized counter. We set the counter's value to 0 to initialize it. So the increment method increments C, the decrement function decrements C, and the value function returns the value of C. Now with synchronized methods, what happens is that when one thread gets to call a method like increment, it shuts out all other threads from accessing any other method while it has the lock for synchronized counters. So basically with synchronized methods, there's a lock associated with each object. And when you call the synchronized method and you're granted the lock, then you are able to execute that method. And while you have the lock, no one else can execute a method in that object until you release the lock. And the way you release the lock is you exit the method. Now, these are called re-entrant locks, which means that as long as you own the lock, you can call another method in this object. So for example, I could call increment, and increment could recursively call the value function to return it. That's legitimate. It's a re-entrant lock. Because you own the lock, you are allowed to call other methods recursively. So these methods are allowed to be recursive, or not even recursive. They're just allowed to call each other. So right now, increment is void, but it could return an int. And the way it might do that is by returning a call to the value function. That would be okay. So you might think, why is this necessary? Because this is a one-line function. Surely there couldn't be any problem with allowing one method to call increment and another a moment later to call decrement. But C++ and C++ aren't as simple as they look. In fact, they involve 3 steps: a retrieving of the current value, an increment or a decrement of the retrieved value by 1, and then a store back to that variable. So let's say you don't use synchronized methods. Here is what could happen. So A calls the increment method, and thread B calls the decrement method. So thread A gets the CPU and it retrieves C. Then it's kicked off the CPU and B gets the CPU and it retrieves C. Okay, so, and the value of C is 0. So now A increments the value it got, and it's in register, it is 1. And B now gets the CPU and it decrements its retrieved value, which was 0, so it puts -1 in its register. Now A gets the CPU and it stores its result in C, making C 1. And finally, B gets the CPU and it stores its result in C, and C is now -1, which, as you can imagine, is the wrong result. The result should have been 0 because A incremented C and B decremented C, so the final result should have been 0, but it's not, it's -1. And that's because of the contention for the same resource and the fact that the two were interfering with each other's operation. So this synchronized method stops that kind of contention.
So
Yeah.
we don't have a mutex in Java. We have methods that are mutually exclusive.
Yes, so that was one of the things that Java did introduce later. It later introduced the notion of locks and mutex, but initially it didn't.
And we have to rely on these for our homework?
Correct, yes.
Okay.
So it's not hard, believe me, to implement the homework using it. So, so actually, to be honest though, I think this is a mutex. I'm not a concurrency guru, so I have to admit that I did not look up mutex before, but this, I think, is implementing a mutex right here. So I take it back. I think it's on an object, so it's not more granular, but we'll show you more granular in a moment.
Well, does this method essentially make whatever happens in the method atomic, or?
Yes. It
Okay.
makes whatever happens in the method atomic, because nothing else can access the method until this method has finished executing. So it makes the method atomic.
Okay. So there's a question in chat that asks, what happens if you call a non-synchronized method from a synchronized one?
Then you still have the, okay, so from a synchronized one is fine because you still have the lock. And I think the real question is, okay, I think the real question should be, is this. Let's say I have a synchronized method, X, and a non-synchronized method, Y. Then my understanding, okay, and what X somewhere in its body calls Y. And so thread A calls X, and thread B calls Y. My understanding is, first of all, yes, you can call Y from X, no trouble. But I think not only can X call Y, but I think that while X is running, I think B is allowed to call Y because it's a non-synchronized method. So my belief is that you can call non-synchronized method, you can call both synchronized and non-synchronized methods from a synchronized method. But in addition, other threads still have the ability to call non-synchronized methods, even while you hold the lock. That's my understanding. Okay? Other questions? Okay, now with these locks, when execution of a method finishes, it is guaranteed that everything is written to memory. So it won't, sometimes for efficiency, compilers hold results temporarily in registers and won't write them back to memory. A synchronized method guarantees that when it exits, any variables it's changed are flushed to memory, so that when something else now accesses this object, it is guaranteed to get the updated results. Okay, so the problem with synchronized methods is that they are very coarse-grained. So they essentially, while that method is executing, they prevent any other thread from accessing any of the synchronized methods in that object. So a more fine-grained way to do synchronization is with synchronized statements, and it starts with the synchronized keyword. Okay, there we go. Synchronized keyword. And it's a block within a method. Notice that the method itself is not synchronized. Only this portion of the code is. And this is grabbing the lock for this object. So while it has the lock, it executes these two statements. But then after it exits the synchronized block, this statement right here is executed in non-synchronized mode. So as soon as I exit this synchronized block, any other method is allowed to call add name and execute it. Okay, so I could be put to sleep after the end of this synchronized block, and then some other thread would be able to call add name and do its own add name and might actually end up adding its name to the name list before me. Okay, so synchronized statements are finer grained, have a single, you specify the name of an object, so that gives you the lock. And just like synchronized methods, they write out the results of their changes to memory. So last name and name count, those changes will be written to memory before the next thread is able to access them. Okay, so here's an example where I use multiple locks, and remember, Java later introduced a more sophisticated form of locking. We'll get to that in a couple weeks. But the original form, the locks were crude and were associated with objects. So if you wanted to get separate locks, you effectively had to create separate objects. So here we're counting the election ballots for 2 candidates. And you can see that incrementing candidates 1's count does not interfere with incrementing candidates 2 counts. So we don't want to use synchronized methods because that would slow down the counting process, because thread A might want to update the vote count for candidate 1, and thread B might want to update the candidate count for candidate 2, and they're not conflicting with each other. But if I make inc1 and inc2 synchronized methods, then as thread A updates the vote tally for candidate 1, thread B is idling. It can't get in there, which is undesirable. So what we want to do in this case is use 2 different synchronized blocks, one in inc1 and one in inc2, and we have them grab different locks. So A, when it calls inc1, will end up grabbing lock 1, and B, when it calls inc2, will grab lock 2. So that ensures that 2 threads can't simultaneously update the vote tally for candidate 1 or for candidate 2, but it does mean that they can, 2 threads can separately update, in parallel, one can update candidate 1's vote tally and one can update candidate's 2 vote tally. So synchronized gives us finer grained control over synchronization than synchronized methods. Okay, and this just summarizes what I was talking about. So both of them force all of a thread's variables to be updated from main memory on method entry and flush those changes to the thread's variables on method exit. And they both require the obtaining and releasing of a lock on an object. So the third way of doing synchronization was in fact introduced in Java's later releases. So this is one of the items available from Java's high-level concurrency package. You get it from java.util.concurrent.atomic, and these are atomic variables that may be updated atomically. So there's a number of them. One is called atomic counter, has these 3 public methods, increment, decrement, and value. And it does exactly what, I'm sorry, got that wrong. This is a class I created. The variable being provided by the Java concurrent util package is atomic integer. So I'm assigning it initially a value of 0. Then this atomic integer class has an increment and get method, a decrement and get method, and a get method. So it will atomically implement the increment and getting. The decrement will atomically implement the decrement and getting, making them atomic operations. So atomic means that the entire operation is performed to completion before any other thread can access that resource. That's the meaning of an atomic operation. Okay, so an atomic operation is allowed to consist of multiple statements, but all statements must be completed before another thread may access that resource. So if you go to java.util.concurrent.atomic, you will see a number of such things. So actually, let's go to it. So you can see it has a bunch of things: atomic Boolean, atomic integer array. There's a whole bunch of different atomic variables. So it's very fine-grained. It only helps you with certain, common operations that you want to do synchronously. So that stops you from having to constantly write your own classes to do these very simple operations. So atomic variables are a third way to make this happen. Okay, questions thus far about how we synchronize? We've seen 3 techniques, one with synchronized methods, one with synchronized statements, and one with atomic variables. Okay. So now there is so we talked about how you might want to be able to put in place happens before relationships. So what we want to do is we want to coordinate actions so that one action happens before another. And I'm going to defer deadlock, starvation, and live lock for a moment. So we will talk about those on Tuesday. What I just want to talk about next is how you can coordinate 2 threads so that they say mutually coordinate their actions on how they access a resource. And you've already seen that you can do it with join. That can force one thread to finish before another thread resumes execution. And of course, simply waiting to fork a thread until another thread has finished is another way. But a third way is to use wait. So when you call the wait method, it suspends your execution until another thread calls either notify all or notify. So for example, the classic situation is the producer-consumer problem, where the producer has to wait until the queue has availability before it adds something to a queue. And conversely, a consumer needs to wait to consume something until the queue is not empty. So the common shared resource is a queue. So basically, you have a queue. So this is a classic that's called the producer-consumer problem. So you have this shared resource, which is essentially a queue, a fixed size queue. So we'll say 3 elements. So initially the queue is empty, meaning that if a consumer wants to get something from the queue, it's empty, so it has to wait until, whereas initially the producer facing an empty queue can add something to the queue, say 3, a number. Now, let's say the producer is quick and it puts in 3 more numbers and it wants to put in a 4th, but at this point it's full, so the producer has to wait because the queue is full. But now the consumer doesn't have to wait. The consumer can remove 3. So it removes 3. And when it does so, it notifies the producer that the queue is, again, that something has happened. The producer did likewise. When the producer added 3, 8, and 10, each time it added one element to the queue, it also called notify to indicate that there was something in the queue. So they're sharing this queue. The queue is a shared resource. And there may be multiple producers and multiple consumers. Okay, here I'm just showing one consumer and one producer, but they may be multiple consumers and multiple producers. So the consumer waits on an empty queue. And the producer waits on a full queue. Okay, so the wait method allows us to wait until some condition has been satisfied. And notify all or notify allows us to resume execution. Now, we have to check the condition because notify all and notify doesn't A, notify us which condition has changed, and B, doesn't guarantee that someone else hasn't slipped into that queue and done already either acquired the resource or added another resource, thus making the queue full again. So before you do anything, if you're in a multiple consumer, multiple producer situation, you have to check before you actually go doing something to the resource. So we use notify when the mutex can, where only one thread can use the lock, and we use notify all for situations where all threads might usefully continue. So if we only have one producer and one consumer, we would use notify. If we had multiple producers and multiple consumers, we would use notify all. So let's actually take a quick look at the producer consumer example. Not what I want either. Amazing how you can't even get okay. There we go. Okay, so let's actually look at a simple example first before we look at producer consumer. So I'm going to head back here for 1 second. And before we look at producer consumer, we'll look at a simple example first. So here's a simple example where I basically want to wait on a Boolean variable called joy before I actually print out the message joy and efficiency have been achieved. So my first thread calls a method called guarded joy, and it goes into a while loop that is waiting for joy to be set to true. While it's not true, it waits. And when it comes out of the wait, it checks to see if joy has been set to true. And if it has, it exits the loop. It prints out joy and efficiency have been achieved. And then the second thread actually is the one that sets joy to be true. And then it calls notify all in order to print the message. So when I call notify all, now this thread will get scheduled and it will print the message. Now notice if there was multiple threads that could potentially print this message, only one of them should print the message after joy is set to true. Maybe what would happen, let's say that in addition to setting joy or printing this message, it set joy back to false. You would not want then a second thread to come in and just without reservation print joy and efficiency have been achieved. That's why even after the wait, you still check the joy variable. Okay, now let's do the more sophisticated producer-consumer example. So here you saw that queue. They're using the class drop for the queue, and the queue contains exactly one message. So the producer produces a message, and the consumer is going to print the message. So think of drop as like a drop box, where the producer drops off a message, and the consumer picks up that message and prints it. So if the drop box is empty, the consumer needs to wait until the drop box has a message. Conversely, if the drop box is full, the producer needs to wait. So the drop box has this message, which is the string to be printed, and a Boolean variable indicating whether the drop box is empty or full. So we have a synchronized method string, take, that is called by the consumer. So while the drop box is empty, we wait. Okay, when it's not empty, we set the status to true because we are removing the one message and notifying the producer that the drop box is empty. And finally, we return the message to the consumer. Okay, then the producer will be calling the put method, and it's also synchronized. So the producer has to wait until the drop box is empty. So while it's not empty, it waits. When it finally becomes empty, it indicates that it has put a message into the drop box by setting empty to false, stores the message in the drop box, and notifies the consumer that the status of the drop box has changed. Okay, so this is the shared resource, drop. It's not in a thread. Notice there's no thread for drop. It's just a shared resource with synchronized methods. Now we're going to create the two thread classes. One is producer. Notice it implements runnable. So it has a pointer to the drop box, which is passed to it in the constructor. So in the constructor, it gets a pointer to the drop box. And it's going to ultimately put these four messages into the drop box. So it is getting a random number generator so that it can generate a random amount of time between its prints. It iterates through the array, and each time it tries to put the message into the drop box. And then when it's done, it sleeps for some random period of time between 0 and 5 seconds. Okay, and after sleeping, it comes back and puts another, or tries to put another message into the drop box, and it may have to wait. Okay, so that is the producer. The consumer also implements a runnable, also gets a pointer to the drop box. Its run method tries to get a message, and if the message is equal done, it's going to finish. So when the producer puts done into the drop box, we're finished. Okay? And otherwise, so we're in a for loop, we just do another take otherwise. And when we get the message back, we print it out. And then we also sleep for some random amount of time, or for between 0 and 5 seconds. Okay, and then finally, this is the glue class. Remember in GUIs we had the glue class? Same thing here. We have actually 4 classes in play: the Dropbox, the consumer class, the producer class, and then our glue class that creates an instance of each of the other classes. So in main, it creates an instance of the drop class. Then it creates a new thread with the producer and starts it, and a new thread with the consumer and starts it. Okay. So you are going to be doing something a little bit similar in the next homework assignment, but since you all are concentrated on Python right now, I'm going to put off the discussion of how you will use this Dropbox metaphor until Tuesday. So on Tuesday, we're going to go over how you use this kind of sharing of a resource in the for keeping a scoreboard for a race. Any questions about this? Okay. So the last thing I wanted to talk about today, before I let you all go, is this is the final way that you can kind of get a happens before relationship, and that is using something called volatile variables in Java. So you declare the variable to be volatile, and you may remember that we talked about volatile variables in exception handling earlier in the course in the context of a C set jump and long jump command. And at that time we said that if you used a long jump command in C, the problem was that stacked frames got popped, and that might include variables temporarily stored in registers, and their values would never be written out. The way you stop that in C from happening is you declared a variable to be volatile. And that meant that as soon as a change was made to the variable, that change had to be written to memory. It could not simply be kept temporarily in a register. And that is the same behavior that happens in Java. If you declare a variable to be volatile, then anytime you make a change to that variable, it must be immediately written to memory. It can't be held in a register. It can be held in a register, but it must also be immediately written to memory so that other threads will immediately see that change. If you don't declare a method or a variable to be volatile, then 2 threads might end up, what could happen, let's say that you have 2 threads, again, A and B. So you have A and you have B, and you have this int variable X. It's 0 initially. So A starts executing and it sets X to 3. But because it's not a volatile variable, Java doesn't write it out. and it leaves it in a register. And at some point, A pauses, and B starts up, and it writes X. And it ends up writing 0 because this 3 hasn't yet been committed. It's still sitting in the register. So if instead I had declared it as a volatile variable, then when I set X to 3, it would be forced out to memory. And when I write X and B, it actually would write out 3. I'm not a big fan of volatile variables because it doesn't solve race conditions. If B executes before A, it will still print out 0. So it's a very weak form of, a very weak way of enforcing happen before relationships. So it certainly guarantees that if A has written to that variable x1, that B will see the result. But there's no guarantee, unless A and B are coordinating their actions, that B will execute its write after A executes its read. So that's why I say volatile variables aren't a particularly good way to enforce a happens before relationship. Join, fork, and wait are much better for synchronizing the actions, or not for ensuring that one thread does something before a second thread does something. So you should know that volatile variables are sometimes used to try to enforce a happens before relationship. But the only thing it's really ensuring is that as soon as a variable is written or is changed, that change is visible to all other threads. That's all it's doing. But it can't control the order in which changes are made to that variable, or the order in which accesses are made to that variable. So if you want to control that, then you need to use fork or join or wait. And when I say fork, what I mean is the creation of a thread and calling it start method. So effectively, I'm being a little bit, I know fork has different meanings. So when I say fork, what I mean is calling a thread's start method. Because fork is going to have other meanings later on, but right now, that's what I mean. Fork means calling a thread start method. It means forking a thread. Okay, so quick recap of what we did today. We started by talking about threads and what they are, and then how to fork a thread and how to control it with sleep and with the interrupt methods. Then we talked about some ways of controlling access to a resource to avoid race conditions and memory inconsistency. And the 3 techniques that we talked about were synchronized methods, synchronized statements, and atomic variables. Okay. Then we also talked about how we sequence 2 threads, how we make thread A occur before thread B. And there were 3 ways to do that, with fork, join, and wait. Okay, so that's your basic introduction to Java's concurrency. So on Tuesday, we're going to talk a bit about the homework assignment. We're going to talk about deadlock. and then we're probably going to start talking about sockets. So with that, I am going to let you go. Wish you a nice weekend. If you have questions, feel free